Thank you. Thanks a lot for the introduction, and thanks for inviting me. It's really a great pleasure for me to speak here. And yeah, I mean, it's, such a you guys are such a powerhouse here in Amsterdam. It's really an emotional moment for me to speak here. Yeah. Okay. So first of all, I'm Giulio. Again, my handwriting is terrible, and it gets worse as my presentation progresses. So please interrupt me. And a few more announcements. So first of all, I have mostly a classical crypto background. So I'm sort of new to this quantum business. So yeah, if I say something silly, please forgive me. And the second thing is that I was told that I should advertise my openings in our group. And the other PI that I'm planning to collaborate is Michel Walter, Michael. I call him Michael Walter. I was told it's funny when I call him Michael Walter, but yeah, it was here. We have openings for PhD students and postdocs. Okay, so good. So today I'm going to talk about obfuscating quantum circuits. It's this is based on a work with James Bartuszek from UC Berkeley, which has appeared at ITCS 2022 and also at QIP 2022. And essentially, the objective of my talk is to sort of motivate you to, think about this problem, and hopefully by the end of the talk, you'll be convinced that it's sort of an interesting problem to think about. First, I'm going to do a bit of introduction, and I'm not going to assume any background in cryptography. So I'm going to say a lot of basic things, but so if I'm going too slow, if you guys already know about this stuff, please tell me, and I'll speed up quickly. So what we want to do really is to literally obfuscate a quantum circuit. What do we mean by obfuscating? Well, let's start with some sort of let's start with the easier goal with obfuscating a classical circuit. Essentially, we want to take a circuit, and I'm going to use circuit versus program versus Turing machine somewhat interchangeably, not really important the representation of your computation. We want to take a circuit and obfuscate it, create another version of a circuit, which I'm going to call C tilde. And the important thing is that, of course, my obfuscation should not change the behavior of this program. And I'm going to say that C is equivalent to C tilde, meaning that for all input X, C of X must be equal to C tilde of X. So this is sort of the intuitive requirement. It says that whenever you're obfuscating a circuit, you're not changing the functionality of it. But of course, we want to do something more than just creating a copy of the circuit. We want to sort of scramble it and make it unintelligible for anyone who is sort of looking at the wires of the circuit. And again, maybe for the moment, it's useful to think about this as just classical circuits or classical programs. So now the question is how to define security, or how to define what we mean formally by an obfuscated circuit. And this is already a non-trivial task. And first, let me first define something which is not really the right definition, but it's sort of a good first step for a definition of obfuscation. This is called virtual black box obfuscation. Or this is referred to as VBB, obfuscation. I think it's a definition from a paper of Barak et al. Already in 2001. In 2001 already. That's something that they studied already 20 years ago. Anyway, so this definition says that for all polynomial size circuits, polynomial side adversaries, there exists an efficient, and by efficient I mean polynomial time, simulator S such that for all circuits C, with too many quantifiers, but I'll get there. Probability that the adversary input the obfuscated circuit returns 1 minus the probability that the simulator with oracle access to the circuit, the security parameter returns 1 is close to 0. And using a bit of a sloppy notation here, but for those of you who know what a negligible function is, it should be a negligible function. Let's say, think of it as just 0. So what does this definition mean? Well, basically, this definition says that you take any adversary who is playing against the game of obfuscation, right? So this guy wants to essentially distinguish different obfuscated circuits. You're giving an obfuscation of a given circuit C, and then you're asking the adversary to output something. It could be 0 or 1. That loss of generality a bit. And we're saying that for any such adversary, there exists an efficient simulator that is able to replicate the output of the adversary without being given as input the circuit, but just querying the circuit as an oracle. So the only thing that the simulator has access to is just input-output behavior of the circuit. So this definition sort of tells you that since these two outputs are computationally indistinguishable, or like they will be almost always the same, the information that the adversary gets from an obfuscation of a circuit C is sort of the same as a simulator would get from an oracle access to the circuit C, right? And of course, we must give this this leakage because I can always query my obfuscated circuit on a given input and learn the output of it. So that's sort of like a necessary thing to do. This definition captures that you shouldn't learn more than that. Okay. So good. So this is the initial definition. Well, it turns out, unfortunately, that this definition is impossible to achieve. And this was shown classically in the paper of Barak. And more recently, it was shown that it's impossible. It was shown that this definition is unachievable even if you are willing to let the obfuscator being a BQP machine. And this is actually the work of some people. Cryptographic. Okay, so what does it mean that this is impossible? It just means that there exists some class of circuit C that are unobfuscatable, so that for which this definition cannot possibly be achieved. So there's always like, you can describe an attacker such that is unsimulatable, the output of the attack. Okay, so good. Now, since this is impossible, what can we do? Well, the thing that people did is sort of settle for the best possible definition after this, and that's the notion of indistinguishability obfuscation. Bit of a mouthful, but people just call this I/O. Indistinguishability obfuscation. And this notion is really just motivated by the fact that this is impossible to achieve. So this is what we want, but we don't have it, so we have to settle for the next best possible. And the security is sort of a bit contrived. Why this would be a good security definition, but maybe I can motivate it. I can motivate it after I write it down. So the security just says that for all C1, C2, so I want to take two circuits which are functionally equivalent. Again, this notion just means that they have the same input-output behavior, but they might, have different wires connected in different ways, or like you could, insert like a for loop that doesn't do anything, right? But it doesn't change the functionality of the circuit. Right. So for all functional equivalent circuit, the obfuscation of a circuit C1 is computationally indistinguishable from the obfuscation of a circuit C2. This is really the guarantee that we want. And well, again, here I'm using a bit of a sloppy notation, but what that means is that just that the probability that the adversary on input an obfuscated version of C1 outputs 1 minus the same, except we give C2, that's approximately 0. Okay, so I'm just going to use the shorthand. I wrote it here just to make it more similar to that definition. But this is really what we want. Okay, so it's pretty similar, it's pretty easy to define. And it sounds like a little awkward as a definition because we're only requiring that the obfuscation of two circuits which are functionally equivalent, that they are computationally indistinguishable. So it seems at first unclear how to use this notion. Even it doesn't sound like something immediately. But maybe if you squint a bit, you'll agree with me that this is sort of the best possible notion of obfuscation. There is a way in which you can actually prove that mathematically, but maybe on a more intuitive level, this is just saying that the obfuscation of your circuit C1 is sort of as good as it can possibly be, right? So imagine that this circuit C2 was already like very good obfuscation of the circuit. This is really just tells you that for all circuits C2, their obfuscations are computationally distinguishable. So computationally distinguishable from the best possible notion of obfuscation. Okay. Good. Yes.
But also from reverse.
Sorry.
The same argument you can make if it's also indistinguishable from reverse.
Yeah. Yes. I mean, well, it's sort of not really for the worse, right? Because like you're not saying it's indistinguishable from C2. It's just indistinguishable from an obfuscation of C2, right?
Obfuscation can make it sort of more obfuscated or less obfuscated.
So there is actually a way. I mean, you can actually prove a theorem that this is the best possible notion of obfuscation. So, and the intuition there is sort of that you could, if there was a better notion of obfuscation, this notion would be indistinguishable from that notion. Sort of the gist, but I don't want to talk too much about that. So yeah, hopefully the gist is clear. Yes.
So is it then enough to think about obfuscations with just functions? Like, is it still necessary to think about circuits?
No, I mean, circuit is just convenient to work with, but I mean,
here you're saying it doesn't matter. Like, all that matters here is what it does, not so much.
Yeah, but you still need to work with something, right? I mean, what do you mean?
That something could be the function that's computed by the circuit.
Oh yeah. I mean, you need to work in a model, right? My computational model is just circuits, right? But you could place a Turing machine here. The definition would make sense as well.
Okay.
I mean, function has to be efficiently computable. For example, like I don't know what happens if you put there, for example, like a function with a continuous domain.
Okay.
We're always talking about Turing machines. Equivalent representations.
Also, the role of the circuit size, I guess, starts a little bit on the right, but I guess it's also two circuits that are the same size.
Yeah, sorry. Yeah. So, well, you can always like add one. So, but that's typically omitted. But I guess in the same way as like encryption, you encrypt messages of the same size. You have to obfuscate circuit of the same size. Otherwise, you can just tell from the size of the obfuscated circuit. More questions. I think now is a good moment for good. Okay, so this is the definition of obfuscation, and I don't want to do too much of a long story, but it turns out that this thing is actually very useful. In 2013, there was a very surprising work from Garg et al., where they show the first candidate construction of indistinguishability obfuscation for all polynomial size circuits. And that was sort of a surprising moment for cryptography. And then people sort of jumped on this train, and like the next 10 years have seen sort of a surge of application of this thing. And it turns out that indistinguishability obfuscation is sort of like, it sort of emerged as the most powerful thing you can do in cryptography. You know, you take your favorite cryptographic primitive, fully homomorphic encryption. You know, I can do it with obfuscation. You take, you know, non-interactive key exchange. I can do it with obfuscation. Some people say it's the crypto complete primitive, maybe a bit of marketing there, but you know, that doesn't necessarily mean anything. But you know, like it's a very powerful thing. Functional encryption, we know how to do it from obfuscation. In fact, we know it's equivalent to obfuscation. Yeah, and it's a very powerful thing. It's something that we like to construct because we sort of get all these other things as corollary. Okay. All right, I'm cheating a bit, but that's sort of the hard part. Well, in a sort of a dramatic sequence of events, a work from last year constructed the first indistinguishability obfuscation from good and well-founded assumptions. So previously the construction of indistinguishability obfuscation were based on sort of new problems. They are hard, they are not hard, we don't know yet, but there was this result that established that, you know, indistinguishability obfuscation, I/O, exists from good assumptions. Unfortunately for us is that construction is based on hard problems over bilinear pairings, and they are quantumly broken, just related to this the same way as you can solve discrete logarithm, you can solve these problems. So for us quantum aficionados, that doesn't really cut it. But there are candidate constructions that, you know, plausibly withstand quantum attacks. So maybe they're not based on as nice assumption as the pre-quantum one, but there are candidate construction for this. Good. And well, basically what we want to do, we want to put the word quantum everywhere, right? Now, you know, this definition is perfectly sensible if instead of a classical circuit C1, we consider a quantum circuit C1. And same goes for C2. One thing that we have to be a little bit careful about is that now, of course, if you're using quantum to sort of obfuscate circuit, we should allow also the adversary to be a quantum polynomial time machine. That seems fair enough. But that's it. Like this is literally the definition for quantum obfuscation. So you know the classical one, you know the quantum. Okay. In terms of functional equivalence, it's for quantum circuits is a little bit more tricky than for classical circuits, because classical circuits can always be randomized, right? I can always consider a deterministic circuit, whereas quantum circuits in general not. So if you want to define it in full generality, you have to work a little bit harder, but maybe this is not super important for this talk. Good. So now this, I think, is sort of like a good survey of the state of the art in terms of classical obfuscation. And now the question is, what do we know in terms of quantum obfuscation? As this question we studied. The answer is yes. So this problem has been defined by Alagic and Pepperman in 2016. So they gave like sort of the definitional background for this notion, and they showed a few applications. Most prominently, an application of quantum obfuscation is so applications. By applications, I always mean like cryptography that we can construct starting from obfuscation. But their favorite application was witness encryption for QMA. And I am going to talk later a bit more about this, but this was sort of emerged as like a cool application of quantum obfuscation. It is known that classical obfuscation implies witness encryption for MP, so maybe it's not that surprising that quantum obfuscation gives you witness encryption for QMA. Again, we're going to talk about what this primitive is. But then the question is, of course, you know, It's fantastic. We have a great applications, but what about constructions? Well, there are exactly two constructions to the best of my knowledge. So the first construction is a perfect obfuscation. For a very limited class of circuits. For limited classes. And I don't recall exactly what the class is, but the point is that this is a perfect obfuscation. By perfect obfuscation, I mean that this quantity here is exactly 0. Okay, and so it's not based on any computational assumption. And there is no way that we can hope to sort of lift this approach to more general classes, definitely not for VQP, because perfect obfuscation cannot work for all circuits unless P is equal to NP, or like VQP is equal to QM in this case. At least in the classical settings, the existence of a perfect obfuscator implies that P is not equal, because sort of solves an NP complete problem, which is like find the minimal representation of a circuit. So there's no hope that this at least with perfect security, obfuscation can exist for all polynomial size circuits. There's another paper that constructs it from, oh, sorry, maybe I should. AJJ 14 and broadband 20. Forgot the reference, so I can look it up later. Right. So yeah, and right. So there is another quantum obfuscation for Clifford circuits. So circuits, quantum circuits, generally consist of gates from the Clifford group, plus a very few T gates, Toffoli gates, few T gates. So, and by a few, it's sort of logarithmically many. Okay. So this is already a non-trivial class, which doesn't appear to be simulatable classically. But, oh, this is also BG20. But it's not in principle clear what you use this for. And in particular, it doesn't imply this application in any form. So, that's currently the situation. Again, this is non-trivial, but it's not immediately clear what this family of circuit is useful for, at least in cryptography. And this other approach is, well, we cannot hope to extend it to all circuits. Okay. And now let me tell you. Yeah.
What do you mean by the last thing? Because you're like trying to prove obfuscation and then you take some gates.
Good. So this is maybe. Yeah. So these are the constructions of obfuscation that we know, and the question is, what kind of circuits can you obfuscate?
Oh.
So ideally, you would like for all polynomial size circuits. We don't have that. This is just a limited class of circuits, and this is a circuits that consist of only Clifford gates plus log many T gates. Okay.
For those circuits, you will have like this probabilities you can perfectly.
Say it again.
Like for those gates, you can perfectly obfuscate.
No, not perfectly. There is a computational assumption. Is that the question? No, go on.
Yeah, and which type, like PUV or?
No. This one, indistinguishability obfuscation.
Okay.
And there is good. So perfect means equals 0. Non-perfect means negligible or computational negligible. That means that there has to be like a computational assumption baked in. And in that case, the computational assumption is just the existence of an indistinguishability obfuscator for classical circuits. It's just, that's sort of like, I would say that that's sort of like a necessary assumption. If you're obfuscating quantum circuit under the hood, you're better be obfuscating also classical circuits, right? So that's sort of like a necessary thing. Maybe like you can think of it like as a minimal thing to do. Yeah. So that's the result. That's the state of the art. And yeah, let me. Hopefully, I'm not going too slow. But, what do we do? Our result. Our result is we make 3 assumptions. Assuming first assumption is LWE. And for those of you who are not familiar, this is the learning with errors problem. And it's one of them, maybe the standard hard problem in post-quantum cryptography. I can talk a little bit more about this. For the sake of this talk, it's not really important what this problem is, but maybe just think of it as a sort of like a very standard assumption in cryptography. So we just assume that this problem is hard to solve for all polynomial time, quantum polynomial time machines. Second assumption is that there exists a classical I/O, and classical mean for classical circuits. And again, as I said before, this is sort of the minimal assumption, right? I think we really need that. If not, it will be a bad sign if you're constructing obfuscation for quantum circuit without classical ones. And then the third is a bit sort of a more leap of faith, is a dual mode classical verification of quantum computation protocol, in short CVQC. And I'm going to talk about this thing more in detail later. This is where things get a bit funny, because here's where we start throwing in random oracles and so on. So I would say this is like the assumptions we are less confident in. Anyway, so under these 3 assumptions, there exists I/O for all null quantum circuits. Okay, so well, what is a null quantum circuit? Is a quantum circuit that always rejects. So that's the definition. That's literally the definition of a null circuit. Slightly more precise, a null circuit C is such that for all inputs X, and again, if this is a quantum circuit, you may want to think of this X as a quantum state. Works as well, the definition, but for simplicity, I'm just thinking of it as a classical circuit. But anyway, probability that C of X equals 1 is close to 0. So basically, that's a circuit that always returns 0. It sounds a bit trivial, but it's useful. So there is a bit of a, okay, so here maybe the probability is because we are considering actually quantum circuits, so there is real sort of probability coming out of the measurement of the states, right? So again, for classical circuits, we would have just said that it's always 0. Okay. Right. So it's maybe the question that you may ask is why isn't just this, but this is here's my obfuscation for a null circuit. So this, yes, it does satisfy the definition, but it doesn't satisfy correctness. So we want that the scheme is correct for all quantum circuits, but secure only for null circuits. Okay. So this is a good obfuscation, but it's only correct on null circuits, right? It's not a very interesting one. Okay. So good. And this is what we do. So the result. And surprisingly, maybe this.
Sorry, correct? You mean
that the obfuscation preserves the functionality.
Correct. Yes. So this obfuscation, literally this, doesn't preserve any functionality, right? But yeah, so that's why it's a non-trivial problem. But yeah, we want that the functionality is preserved, but we only ask for security when the circuit is always output 0. That's what we do.
So how do you go from a quantum circuit to a classical bit? Do you just assume you're going to measure
The last register.
Yeah, that's right.
Yeah. Yes. Exactly. More questions? Okay, so I guess maybe the natural question is why do we want to do this? And the reason is that this actually turns out to be implying witness encryption for QMA. So the application that was erased now, but this we show, well, it's actually pretty easy to see that it implies witness encryption for QMA. And along with that, it also implies a series of new cryptographic primitives, which we only know previously we didn't know how to construct them from essentially any assumption. For example, MISIC or QMA. Non-interactive zero knowledge, something that cryptographers care about for all statements in QMA. Something else that you might have heard of is attribute-based encryption. We do it for BQP, so for quantum circuits. And we knew ABE for P, but not for BQP. Now, under this assumption, we know it exists. So if you're happy with this, then we know it exists. Of course, sometimes here we also require the additional assumption of classical I/O. It's already baked in here, but as a general theorem, this thing by itself is not sufficient, but plus I/O, yes, it is sufficient. Good. I'm at the mean time. 35 minutes. Should I leave some room for questions in the end, or should I?
I think we just go on and we'll see.
We'll see. Okay. Okay, good. So maybe now I can show. Now I can show a little bit how to. First, I want to show how to use indistinguishability obfuscation for null circuits. It's a very fun interlude, and then we're going to see more or less the blueprint of our construction, but it's going to be simple. So there's no need to stay concentrated on this. Good. So first of all, what is witness encryption for QMA? Well, it's the following primitive. So it consists of 2 algorithms. So the first algorithm is an encryption algorithm. Takes as input a classical message. Think of it as just a bit for simplicity, and X as an instance of some language L in QMA. Okay. So the encryption algorithm takes as input X. Maybe think of it as this classical description of a statement for some language L in QMA and produces a ciphertext. And naturally, the decryption algorithm takes as input the ciphertext C along with a witness W for X, right? And if the witness W was a valid witness, so namely if the relation X comma W equals 1, then this thing returns the message. Okay, so you can think of this as sort of generalization of the standard notion of public key encryption. For public key encryption, this is a secret key and this is a public key, and the language is your favorite language that implies public key encryption. For example, I mean, it's not really quantum friendly, but RSA. If your language is sort of the RSA encryption scheme, this would be an integer n, and this would be like the factorization of the integer. But this is a very general notion, and it encompasses all encryption scheme, and it turns out to be like a very powerful notion. It implies much more than just public key encryption. And the security is particularly satisfactory to define because it just, the only thing that we require is that for all messages M0 and M1, and for all X not in the language, so instances for which there exists no witness, then we have that the encryption of M0, X is computationally indistinguishable from the encryption of M1, X. This is just saying that if X is a false statement, then the message is hidden.
You said for all that you wrote exists.
Oops, thank you. So very nice to define. Well, so let's say we have obfuscator for null circuits. Then the construction is particularly straightforward. Just have to define the encryption algorithm. Basically, we take the circuit that takes as input quantum state, psi, and checks if relation psi 1 return message and else return 0. I'm using 0 and bot somewhat interchangeable. So I define this circuit, okay? Just give it a name, gamma. And now my encryption is just obfuscation of gamma. That's my ciphertext. Okay. So I know that this is well defined because this is literally the definition of Q&A. There exists an efficiently computable relation such that if you have a state and it's a valid witness for X, then it returns 1 with all sort of overwhelming probability. And yeah, if I can obfuscate this class of circuits, then this is well defined.
Where does psi come from? It returns what psi?
It's the input of the circuit.
Oh, okay.
So that's maybe just think of it as a symbolic evaluation. Well, you can observe that.
But before,
Yes.
just for, it's slightly confused, before you wrote R, X, W, so the psi is the W.
Oh yeah, the size of the
So it's
W.
the other way around. I mean, you
Oh
say
yeah,
the-
sorry.
So the X is still the statement and psi is now the witness.
Yes.
With Q&A, you have the witness is a quantum state.
Thank you. Hopefully I didn't do any. Did I swap? No. Yes. So this is the quantum state is the witness and X is the state. And now, so what does my security require? Again, the security requires that whenever my language, whenever my statement is not in the language, then the encryption is secure. And now note that if X is not in the language, then this never returns 0. Sorry, never returns 1, always returns 0. This means that this is actually a null circuit. And now I can call my obfuscation guarantee to say that this is computationally indistinguishable from an obfuscation of bot, just means circuit that always returns 0. Done. So that's as simple as that. Okay.
So I guess in particular, it's independent of the message. Right? That's why.
Exactly. Yeah. So a good point. So note that the information of the message is somewhere hardwired in gamma, right? So if I'm giving obfuscation of gamma, maybe the information about the message is somewhere in here, whereas here there is no information about the message whatsoever. Okay.
And can you give a little bit of intuition why the security definition for witness encryption might make sense not to have any requirement when X is in the language?
Oh yeah, so
Because you still want it to be secure for someone who doesn't know the witness.
yeah, so it turns out that's a bit tricky to define. I think the reason is that that's sort of the best thing we can do. The reason why that is already sufficient is because maybe you can think of languages for which true statements and false statements are computationally distinguishable. And if you do if you have computationally right, whenever you call the computational indistinguishability of this language, then this thing becomes automatically unsatisfiable, and then the witness
It starts
encryption.
leaking the message, suddenly you find out whether your statement was true or false, which is something that should be hard to compute for.
No, but the message, the message is something I can sample locally. It's not a secret information about the statement itself, right? So if the statement was hard to tell whether it was true or false, it's still hard to tell whether it's true or false also if I compute this witness encryption, right? So this is the public computation, everybody.
Right, so we don't have a guaranteed secure, but it's hard to see the difference between the case where it's secure or not guaranteed to be secure. So it's also secure in the other case.
Yeah, exactly. Like, but you can do this argument formally. I mean, well, that's the typical way in which you use it. You switch to a false statement, and then you are allowed to sort of switch the witness encryption. Yeah. It's very similar to what's happening with the definition that now I raised of obfuscation. You're only allowed to switch whenever the two circuits are equivalent. That is a bit that creates a bit of problems here and there. Yeah. No questions. So hopefully by now I convinced you that sort of this is a powerful tool. Like witness encryption is something very difficult to achieve, and then using null-iO, I just do it like this. So I think it's pretty easy to do. And now let's see how we do null-iO for quantum circuits. Oh yeah, so null-iO, I mean obfuscation for null circuits. And I want to leave some time for listing open problems, which there are a lot. Right, so let me give you sort of the general blueprint of our construction. So it's a three-step construction. So in the first step, right? So in the first step, we are going to consider what is called a classical verification of quantum computation. Again, in short, CVQC, classical verification of quantum computation. This is a protocol which is played by a prover, and the prover is a quantum machine, quantum circuit, whatever your favorite model is. Whereas the verifier is a classical Turing machine, classical circuit, and it has in its head a certain circuit Q, which is a quantum circuit. The protocol proceeds by the verifier computing some public parameters for quantum circuit. Again, this is all classical, right? So just maybe think of just your quantum circuit as like a paper description of a quantum circuit, right? So I can draw a quantum circuit, and so there's nothing quantum happening on this side. And at some point, once the prover receives these public parameters, he's doing some quantum computation locally, and then he produces a proof phi of q x. Again, x is some input, and again, it's a classical proof. Everything is happening classically, and at the end, the verifier outputs y, which is equal to q of x. For this to be meaningful, of course, x needs to be a classical input, y needs to be a classical output, and as we said before, this is obtained by just measuring some predefined register of the circuit. And the amazing thing is that there exists a protocol with exactly this form that allows the verifier to be convinced that this computation was done correctly, even though the verifier is a purely classical machine. Okay, this was again another surprising result by, maybe you heard of this, with Giulio Malavolta And then there's like been a bunch of follow-up works, but this was sort of the first protocol. It was not 2 rounds, but it has been reduced to 2 rounds in follow-up works. And this already gives us sort of an intuition how to do this, right? I mean, now the intuition is the thing we would like to do is say, okay, good. I have no idea how to obfuscate quantum circuits, but I know how to obfuscate classical circuits. So if I could obfuscate this guy, I'm already in business, right? Because I could sort of let the computation happen, in a sort of untrusted environment. But then, as long as I can verify that the computation was done correctly, right? And this, this verification is happening under an obfuscated classical circuits, then this sort of gives me hope to obfuscate the entire quantum circuit. Sort of general blueprint. Now, of course, one immediate problem is that the computation that we are doing here is completely public. So Q is completely public. So there's no secrecy about the circuit Q. But this is actually not that difficult to deal with. There's one thing which is called quantum fully homomorphic encryption. I'm sure many people in this room know more than me about it. Quantum fully homomorphic encryption basically allows you to encrypt any classical message X. Just use M, and then using a public algorithm, compute another encryption of some function f of m. And f can be a quantum circuit. Okay. If this was just a classical circuit, that would be just fully homomorphic encryption. So the solution is relatively straightforward. Once you have this tool, you basically just encrypt everything under a QFHE encryption scheme. And the key of the QFHE is held at the verifier side. So the verifier knows the key of the QFHE. So he knows how to decrypt. The prover doesn't know how to decrypt, but he can sort of run the same computation by just running the same operation homomorphic, right? So the effect of this layer that we're adding, so this was sort of step 2. Okay. The effect of this layer is that the prover is doing exactly the same computation as before, but obliviously, right? He doesn't know what Q is, yet he is able to do exactly the same computation by the correctness of the fully homomorphic encryption scheme. And of course, here, the difference is that we're getting a ciphertext. So first we have to decrypt it. And then we can recompute the output. Okay, so this is just adding a layer of fully homomorphic encryption. Okay. Or it's here. And then, well, essentially the last step is to just obfuscate. And well, now you can observe that this is a completely classical algorithm. So this is a well-defined operation, just using some classical obfuscations. Okay. Well, let's say I'm just, for my convenience, I'm just pre-computing the first message. So, so obfuscation just makes sense for non-interactive circuits, right? So what I'm doing, I'm just pre-computing the first message and then obfuscating the circuit that goes from here to here. That's just like one input output circuit. So QFHE. Okay, and I'm calling this B prime. I'm calling this B. Okay. So how do I evaluate the circuit? Well, I basically run the prover algorithm homomorphically, and that will result in some ciphertext C, and then I feed this ciphertext into this classical obfuscated circuit, and whatever the circuit returns, I return. Okay, so this is the scheme, but yeah, unfortunately, it's not that easy to prove that this is actually secure. How much time do I have? Oh, okay, maybe I'll just give you like an intuition why this is not easy to prove. And and then I just go with the open problems. I mean, I want to bore you too much. But this is basically the outline of the scheme. Now the problem is that the source of all problems is that if you recall the security of this obfuscation here, so the classical obfuscation is that we can call this, can do this switch from one circuit to another only when the two circuits are functionally equivalent, right? Now, ideally, we would like to say, okay, we're going to switch this circuit, this obfuscated circuit, into an obfuscation of a circuit that always returns bot, right? So it always returns 0. Ideally, that's the step that we would like to do. Now, the problem is that this circuit is not a null circuit. In particular, it will return 1 or non-zero in many, many positions, right? So the problem is that proofs for this CVQC, they exist. They are just hard to find, right? So in particular, this protocol is only computationally sound. So we know that these proofs exist. So if you had an unbounded, machine, you could always find this proof. But we know that they are also hard to find, because if you do it, you are breaking some computational assumption. But obfuscation doesn't care about being hard to find versus existing. So we really need to move into a world where such proofs do not exist, right? And one option would have been to sort of design a protocol, a CVQC protocol, for which that's the case. And I think there is negative evidence that such thing is possible, because it would imply sort of a classical verification of quantum computation without computational assumption. And I think people believe that that's not possible. But we work around this issue, and maybe I'll refer you to the paper for more details. But this is basically the general blueprint on how we obtain the result. And good, open problems. So questions? So we'll start with three. Okay, good. So yeah, so you might have noticed that this approach here, I claim will secure only for null circuits, but syntactically this also works for all circuits. There is no, nothing that prevents me in principle to run this scheme for any also not null circuit, and maybe I can say, okay, maybe that's secure. So it turns out it's not. Like there is an explicit attack if we fit into this blueprint a circuit which is not null. So main open question is find any construction of QIO. Literally any. So, I'm not picking with computational assumption. If you cannot prove it, it's also fine, as long as you cannot attack it by just looking at it. Okay, so literally anything. We don't know anything in this. So I'm not even asking you for like a mathematical proof. So something that I cannot break like this. And yeah, so this is open. I mentioned that we needed something called dual mode CVQC, which is sort of what we construct to go around that problem that I said before. But we need like sort of a bit of a sketchy assumption, and this is discussed more in the paper, but we need to assume some oracles there. And so the question is construct dual mode CVQC from standard assumption. Standard assumption. Standard assumptions, for example, LWE, I'll be happy with LWE. And then, if I can remove this, I will be very happy, because LWE is sort of, we trust it. Classical I/O is to some extent necessary. So I'd like to remove sort of this line. Another question is, this is just one way to construct witness encryption, maybe not, not a particularly sophisticated one. So maybe one could hope to construct witness encryption directly from sort of better assumptions. Maybe you don't have to go through this route of obfuscating null circuits. Completely open, and I mean, of course, any other applications like NASIC for QMA, ABE, all the stuff that I said before, completely open from any assumption, which is not this thing. Maybe one thing that I should be precise here is when I say NASIC, non-interactive zero knowledge, I mean publicly verifiable non-interactive zero knowledge. If you are okay with privately verifiable, there are other protocols. But publicly verifiable, which is sort of what people would typically want, can only do it like this. Yeah, so there is also there is maybe I'll skip that, but there's also sort of like a nice technical question about construction of quantum I/O for not null circuits, for circuits that output 1 sometimes. There, the question is really just about verifying quantum computation in a way which is sort of reusably secure. What do I mean? So one problem is that an interactive protocol, I can always assume that at some point the verifier stops responding, right? So it's an interactive protocol, the verifier will not respond twice. You cannot rewind the verifier in an interactive protocol. But whenever I'm obfuscating a circuit, you can do whatever you want with it, right? You can query it on an input, see what it does, then query it adaptively on another input. Over the internet, at some point, I'll stop responding, right? So, and the problem is that those protocols are secure in the quote-unquote internet settings, where I can control what I'm doing. But whenever I'm obfuscating something, I sort of lose control over my circuit. And in that settings, things are insecure. So like the nice technical question is, can you construct a CVQC? And in fact, even not classical, I think it's not known. Even if you allow the verifier to do some quantum operation, right? Yeah, construct a protocol to verify quantum computation in that settings, and is secure in these reusable settings. Yeah, I guess that's all I have to say. Thanks for your attention. I'm happy to take questions.